Lesson 12:7, Probability of Compound Events. Our essential question is, how do you calculate the probability of compound events? So our first vocab word is compound events. Compound events means two or more events. We worked in chapter 5 with compound inequalities, and that was when we had two or more inequalities. So compound means two or more. Independent events, what that means is that the outcome of the first event does not affect the outcome of the second event. So you can think of the two events as being independent from one another. So to find the probability of both events, A and B, happening, you can just multiply together the probability of event A times the probability of event B. So they have nothing in common, they don't affect each other, so you multiply together their probabilities to get the probability of both events happening. Now, dependent events, these events are different. The outcome of the first event does affect the outcome of the second event. So we say that the probability of event A and B happening is the probability of A times the probability of B following A. So that's kind of our way of saying that A has some effect on B. So because A happened, then the probability of B is a little bit different. You still multiply the two probabilities together, though. Okay, we're going to try this out. We have a bag that contains these marbles. There are 6 black marbles, 2 green marbles, 9 red marbles, and 4 yellow marbles. A marble is selected, and then it's replaced. So that means it's put back in the container, and a second marble is selected. So what types of events are these? Are they independent or dependent? Well, the key word here is underlined. The key word is replace. Because the marbles are being replaced each time, that makes these independent events. Okay, so the probability of getting a black marble followed by a yellow marble. Well, the first thing I need to do is figure out how many marbles are there in all. So I need the total number of marbles before we can start talking about these probabilities. So 6 plus 2 plus 9 plus 4 is 21. So the total number of outcomes is 21. So number 1, the probability of black and then yellow. Well, there are 6 black marbles. So 6 black marbles out of 21. That would be the probability if I draw one out, that it would be black. 6 out of 21 are black marbles. Then remember, I'm putting it back in the container. So there are still 21 marbles. The second event we're looking for is yellow. Yellow, there are 4. So 4 out of 21 is the probability, drawing yellow, and then I need to multiply together these probabilities. So remember, when you're multiplying fractions, you multiply straight across. So 6 times 4 is 24, and 21 times 21 is 441. Now, as a fraction in lowest terms,
any 7th graders that are staying for Project Pizza need to report to J111 immediately. 7th graders staying for Project Pizza need to report to room J111 immediately.
Okay, so fraction in lowest terms, I can divide those both by 3. So that gives me 847ths. And if I divide that, I could make it a percent. So it's about 0. Oops, sorry about that. It's about 5.4%. Remember that probabilities can be written as fractions, or they can be written as decimals or percents. So any of those forms. Okay, our next probability. Number 2, we have red and then green. So the probability of drawing red first is 9 21sts. And then we're replacing it, we're putting it back in, so the probability of green is 2 21sts. So if I multiply that, I would get 18 over 441. And if I reduce that, it reduces to 2 49ths. And as a percent, 2 divided by 49, and then I move my decimal point 2 places, it's about 4.1% for number 2. Number 3, not black, and then red. The probability of getting something that is not black. Well, if there are 6 black marbles, and there are 21 marbles in all, 21 minus 6 is 15. The other way to get that, you could add the green, red, and yellow together, you still get 15. So 15 out of 21 are not black. And then the second one, red. Red was 9 out of 21. Now on this one, I'm going to show you how instead of multiplying and getting big numbers, I can do some reducing first. I know that 9 and 21 I can divide by 3. So I can reduce that to 3 over 7. The same thing is true for 15 and 21. If I divide those by 3, I get 5 over 7. So then when I multiply straight across, now this is already reduced to 15 49ths. So you can reduce first by canceling, like from the numerators and denominators, or you can reduce at the end. It doesn't matter. So this one is about 30.6%. And then my last one, yellow, green, red. Now we're talking about 3 different events here. So yellow is 4. So 4 out of 21 are yellow. Then green are 2 out of 21. And red, 9 out of 21. So I'm definitely going to reduce first on this one, because I have 3 fractions, so I'm going to reduce this one, divide by 3, and I get 3, and divide by 3, and I get 7. And then I can divide this 3 and this 21 by 3, and I would get 1 and 7. And that's all the reducing I'm going to be able to do. So my numerator, 4 times 2 is 8, and the denominator, 21 times 7 times 7 is 1,029. 8 divided by 1,029 is about 0.8%. Okay, so these are our first 4 compound probabilities. The next set of examples, a standard deck of cards has 52 cards, 13 of each suit. If you know this, if you're familiar with decks of cards, you don't need to write that information down. It's just for the people who aren't so familiar with cards, you would want to write it down. 13 of each suit, hearts, diamonds, spades, and clubs. And within those suits, you have number cards and face cards. Well, each number or face card in the deck, there are 4 of each, because there's 1 for each suit, hearts, diamonds, spades, and clubs. So we have a card selected, and then it's not replaced. That means that you're not putting it back in the deck. It's like when you deal out cards to people, you keep on dealing. If you deal 1 card, then you deal a 2nd card, the 3rd card, the 4th card. You don't usually put the other cards back in the deck while you're doing that. So a card is selected, it's not replaced, and a 2nd card is selected. So the first question is, what type of events are these? Well, because it says not replaced, these are dependent events. So one event depends on the other one. Find each probability. So number 1, the probability of getting a 2 and then getting a 5. Well, there are 4 cards in the deck that are 2s, because there's a 2 of hearts, 2 of diamonds, 2 of spades, and a 2 of clubs. So 4 out of 52 are 2s. Then you're not putting the card back. And that card was a 2. So the next probability we need is to get a 5 for the next card. Well, there are 4 5s in the deck, but there are only 51 cards because you didn't put that 2 back. Now, this one, I can reduce a little bit first. 4 divided by 4 is 1, and 52 divided by 4 is 13. If I multiply these across, 1 times 4 is 4, and 13 times 51 is 663. If I change this into a percent, it is about 0.6%. So that means it is not very common to get a 2 and then a 5. Good news, because those probably aren't the cards that you were looking for when you're playing cards. Okay, our next one, probability of getting a heart and then a spade. Well, the hearts, there are 13 hearts in the deck out of 52. And then getting a spade. A spade, well, there are 13 spades in the deck, and our first card wasn't a spade, so there's still 13 of them there. But we didn't put the first card back again, so the denominator goes from 52 to 51 because we didn't replace that card. Now, I can divide by 13 to reduce my hearts to 1/4. That should make sense because 1/4 of the deck would be hearts. So that first fraction is 1/4. Now, if I multiply straight across, I get 13, and 51 times 4 is 204. If I divide this to make it a percent, it's about 6.4%. Next one, number 3. Ace, king, queen. Ace, king, queen. All right. There are 4 aces out of 52 cards. Then my second card, I want a king. There are 4 kings, but my denominator goes down to 51 again because I didn't put the ace back in. Then there are 4 queens, and my denominator has to go down again to 50 out of 50 cards. Reducing my fractions, the first one, if I divide by 4, I get 1 and 13. The last one, if I divide by 2, I get 2 and 25. And I think I'm done reducing. So my numerator, 1 times 4 times 2 is 8. And my denominator, 13 times 51 times 25 is a huge number, 16,575. So I'm thinking that when I divide this, I'm going to get a pretty small percent. And I'm definitely right. 0.05%. So that is a very, very small probability of getting an ace, then a king, then a queen. Okay, number 4. Probability of getting an ace, then a card that's not an ace, then an ace again. Okay, so there are 4 aces out of 52 cards. Then, out of the 51 cards remaining, I've got to think about this. There will be 3 more aces. Then the rest of those cards are not aces. So that means 48 out of 51 cards that are left in that deck are not aces. All right, then there are 50 cards left, and 3 of them are aces because my first card was also an ace, so there are only 3 aces left. Now I can do some reducing. First one reduces to 1 and 13. The second one divides by 3, and it reduces to 16 and 17. Then that 16 is an even number, and so is the 50. So I can divide 50 by 2 to get 25 and divide 16 by 2 to get 8. Now I think I've reduced as much as I can. So my numerator, 1 times 8 times 3 is 24, and my denominator, 13 times 17 times 25, 5,525. So dividing this gives me about 0.4%. So very uncommon again. Very uncommon again. To get an ace, not an ace, and then an ace. So basically 2 aces. All right. Moving on. Now we're switching over to rolling a fair die. A fair die is being rolled, find each probability. So just one. So we're rolling just one fair die. Okay, so our first probability that you roll an even number. So a fair die has the numbers 1 to 6 on it. So the probability of getting an even number, 2, 4, and 6 are even, so 3 out of 6, or 1/2, or 50%. The probability of getting at least a 4, so at the very least a 4. So that would mean 4, 5, or 6. So that's 3 outcomes out of 6, 1/2, or 50% again. The probability of getting a number less than 3. Less than 3 would be just 1 or 2. So 2 out of 6, 1/3, or about 33.3, repeating percent. Number 4 and number 5 are compound events. See a little star over here. So a 2 and then a 5. The probability of getting a 2 is 1 out of 6. The probability of rolling a 5 has nothing to do with getting a 2. There's also 1 5 out of 6. So 1 in 36 would be the chances of getting a 2 and then a 5. So those events don't have anything to do with each other. So it's about 2.8%. So those are independent events. The probability of getting a 6 is 1 out of 6. Then the probability of not getting a 6 would be the other 5 numbers. So 5 out of 6. So multiply these across and you get 5 over 36, or about 13.9%. So the wording, so you just have to be careful with the wording. Make sure you understand if they're talking about one single event or 2 events that are compound. Okay, our last slide. Events that are mutually exclusive are events that cannot occur at the same time. So when that happens, the probability of getting A or B is found by adding together their probabilities. Events that are not mutually exclusive are events that can occur at the same time. So there's some overlap. So to find their probabilities, you add together the probability of each event and you subtract the part where they overlap, the probability of A and B. I'm going to explain that for these last 4 examples. So are the events mutually exclusive? Yes or no? Then find the probabilities. So we have 4 left. Okay, mutually exclusive. So are they separate from each other or do they overlap? Hearts or 10s? Ask yourself, is there a card that is both a heart and a 10 at the same time? Yes. So are they mutually exclusive? No, they are not, because there's a 10 of hearts. Probability of 2 or a 5, are they completely separate? Yes. 2s and 5s are all different cards. Spades or clubs? Yes, totally separate. So they're mutually exclusive. Red cards and queens? No, because there are 2 red cards that are also queens. So, hearts or 10s? Hearts or 10s? They're not mutually exclusive. How many hearts are in the deck? 13.
Christine Nelson, please call extension
So 13 out of 52 would be the probability of getting a heart. Plus, there are 4 cards that are 10s, 4 out of 52. But then I have to subtract that 1 card where they overlap. That 1, remember, this 1 right here that I'm subtracting is the 10 of hearts. So it's a heart and 10 at the same time. So I can't count that card twice. So my final answer, 13 plus 4 is 17, minus 1 is 16. So 16 over 52 reduces to 4/13. And 4 divided by 13 is about 30.8%. All right, next one. The next one we said yes. We said yes for. So that means yes, they are mutually exclusive. They're totally separate. So the probability of a 2 or a 5, well, there are 4 2s and there are 4 5s. So the probability of getting a 2 or a 5 means there are 8 out of 52. It reduces to 2/13, which is about 15.4%. So there are no cards that overlap for that one. The same thing for spades or clubs. Spades, there are 13 spades. Clubs, there are 13 clubs. So the probability of drawing a card and getting a spade or a club, that's going to be half of the deck. So 50%. And then the last one, red card or a queen. Well, the red cards are the diamonds and the hearts. So red cards account for 26 out of 52 cards in the deck. Plus there are 4 queens in the deck, but 2 of those queens are red cards. So I have to take away, so these are the 2 queens that are red. You can't count those cards twice. That's where they overlap. Okay, so 26 plus 4 is 30. 30 minus 2 is 28. So 28 over 52 reduces to 7/13. And 7 divided by 13 is about 53.8%. Final answer. All right. So you should be able to write a summary now and answer the essential question and then check with your teacher for your homework assignment.